Hello guys, welcome to my video series on PIC18F programming, and today we're gonna take the steps of making our first project with PIC18F 2550 microcontroller. First things that we do is getting to know MPLAB IDE and how to create and compile your projects. Then I'll give a slight introduction to configuration bits, and finally we test our circuit on Protas, and if things go well we assemble it on a breadboard. So let's start by introducing MPLAB development environment. Okay guys, click on the IDE icon on your desktop. Here it is. It's the start page of the IDE. We're not going to do a lot of things here, so go to File, then New Project, and select Microchip Embedded and a standalone project, then click Next. At this point we're going to choose a microcontroller we're going to write code for. In our case it's a PIC18. Here it is, PIC18 2550, and here it is. Click Next, select Simulator and Next. Then we choose a compiler. It's XTC8. You should already have it installed on your PC. Then click Next. Then we pick up a name for our project. I'll name it Blinky, since we're going to blink an LED constantly on and off. And click Next or Finish. Here it is. So go to Source Files in your project folder Blinky, go to Source Files and then New main.c. This is a file where our C code is going to be written. Name it anything, name it simply main, and then hit Finish. Looks like MPLAB has done the hard work for us by including the xc.h header file, which contains, among other things, the declaration of register names, as we're going to see later. And there is a well-known function, main function, where your program starts execution. And we are ready to write the first lines of code. And we start by writing the configuration bits. Okay, a microcontroller is just like any other system, as it needs some sort of settings, like what features you want to activate and what features you want to deactivate. And in a microcontroller, the most important settings are the oscillator settings. As I said previously, the oscillator determines the speed at which the microcontroller runs your code, but we never mentioned how. We already know that a microcontroller executes a bunch of machine code instructions stored in its program memory, starting from the first instruction, then instruction 2, 3, 4, and 5. But how long does it take to execute a single instruction is what the oscillator speed controls. So let's say that we've connected a 4 MHz oscillator to the microcontroller. Okay guys, you can convince yourselves this is the electrical symbol for the oscillator. And in PIC microcontrollers, whatever oscillator speed you connect is divided by 4. So this microcontroller operates on a 1 MHz speed, because 4 MHz by 4 is just 1 MHz. So this means that this microcontroller can execute 1 million instructions per second, and by doing easy math we can figure out what time it takes to execute a single instruction, which is 1 over f, or the frequency, which is 1 over 1 million, equals 1 microsecond. So this microcontroller executes an instruction every microsecond. And if our program is just 5 instructions, it can execute it in only 4 microseconds. So let's go back to MPLAB and see how we can configure our microcontroller. MPLAB provides an easy way for setting the configuration bits through this window here. And to get it, go to Window and then Target Memory Views and Configuration Bits. And here it is. First thing we can see is something called PLL and this is about the USB module, and leave it at 1 or anything, it doesn't matter. And the next thing is something called CPU diff, and it's very important to leave it at oscillator 1 PLL2 and USB div, leave it at 1. And the most important thing here is something called F oscillator, which controls the mode of the oscillator in this microcontroller. Looking at the data sheet, we can see that this microcontroller has lots of oscillator options, but most prominent here are the XT, which is used for oscillators less than 4 MHz, and HS, high speed for oscillators equal to or greater than 4 MHz. And since our oscillator we are connecting is just 4 MHz, we go for this option. And all the other options here are for the internal oscillator, which we're not using in this project. Okay, let's go back and see the other configuration bits. So we set this to HS, and it's HS. Okay, from this point, all the other stuff are just fancy features of the microcontroller, and we won't bother getting through every single one of them, but you should turn them all off. And one thing to consider here is the watchdog timer, or WDT. Be careful guys, because if you forget to set it off, you will notice that the microcontroller keeps restarting itself every 32 milliseconds. This is because watchdog timer is used to save the microcontroller when it gets stuck. And if you are doing this on purpose, okay, that's okay. But if not, you should turn it off. Okay guys, and move down, make sure that everything is off again. Okay, and here we go. Click on the generate source code to output and copy everything from the top here. Copy everything. Okay, we already included the xc.h file, and click on copy, paste it here. I've already pasted this stuff in my source code, so here it is, and we're ready to start programming for the microcontroller. Okay, this is the code for our project, and this code should keep an LED connected to pin RP0 or pin number 21 in the microcontroller, constantly blinking on and off every 500 milliseconds. Don't worry if some or all of these lines seems off to you. These lines will be our main focus on my next video. But worry about copying and pasting the code given in the description to your main.c file and compile it by hitting the hammer icon here, or go to production, build main project. Oh, it's an error, and no one thought I had a promising future anyway. And this error tells us we haven't declared an identifier called crystal frequency. This is because the delay ms function we use here needs this constant to know what is the speed of the oscillator we're connecting, and we can solve it by writing anywhere above the main function this line, hash define underscore crystal frequency, and 4 million, since we're using a 4 MHz frequency oscillator. And here we go. Let's take the shot and build it again. Oh, don't feel flattered, it's not the hardest of the problems we're going to get. After successfully compiling our first project, let's take a look at some of the statistics here. This is the amount of programming space our code takes up, and it's about 0.1% of the programming space available on this microcontroller, which is reasonable for our literally micro project. And this is the amount of data space or RAM the code consumes, which is 0.1% again. So let's move on to building our test circuit on Protas, and go to Protas, click on it, and click on File, New Project, name it Blinky dot whatever, Blinky, and click Next. Leave it at default, Next, and leave it at do not create a PCB layout, and click Next. No firmware, Next, and Finish. And go to component mode here, click on the P letter. Now we're searching for our microcontroller PIC18F 2550. Luckily we found it, and click OK. Click anywhere on this grid and draw the microcontroller here. Zoom in a little bit. You can move up or down like this to get a proper view. Now let's look for the rest of the components. Go to P again, and we're looking for an LED, of course, so LED. There's a lot of LEDs here, so let's look for appropriate color. Let's take the red one, click OK, and of course we need a resistor for connecting it to the microcontroller, so let's search for a resistor. And oh, that's really lots of resistors, and I don't know, let's take this one. I know it's 30 kilo ohms resistor, but we can change it later. Okay, let's pick up this one and let's connect it. And where's RP0? It's pin number 21 as we said, and connect it to the microcontroller. Click on the pin, and let's take the LED and put it here, and we need the ground, and we can find the ground in terminals mode here, and the ground here it is, and click here, connect it to the LED. And finally we need to upload the code to the microcontroller. Double click on the microcontroller and select the oscillator speed. Fortunately we are using a 4 MHz oscillator, so we don't need to change this number here. And this is a program file. Click on the folder icon here. Now we have to find out where MPLAB saves the binary file resulting from the compilation process. And by default MPLAB saves it in the C drive, users, your username, and then MPLAB X projects, blinky.x, and dist, then default, production, and here it is, the hex file, blinky.x.production. Then we upload the code to the microcontroller by clicking OK. At this point, guys, we're ready to run the simulation. But first, I think many of you guys are asking, where is the power supply and ground connection, or even the oscillator? And in Protas, they are implicitly connected, so we don't have to connect them again. But in real life, of course, we have to connect them. And okay, so we go and click on the triangle button to start the simulation, and we're facing another problem here. The LED is not blinking, but what is this alternating red and blues and red color on RP0 pin? In Protas, blue means 0 volts and red means 5 volts. So apparently RP0 is outputting the correct voltage, 0s and 5s and 0 and so on. So it's not a coding problem, since our code is doing what it's supposed to do, and there is something wrong in the connection. If you've noticed, we use a 30k ohm resistor, which is, you know, very large, that it drops all the voltage, leaving nothing for the LED to light. So the right solution is to change this resistor value and replace it with a smaller one. So first we turn off the simulation. By the way, you cannot change the circuit if the simulation is running. And click on the resistor here, change it to 300 is just fine, and click OK. Then run the simulation again. Wow, the past 15 minutes didn't go for nothing, and we have the LED blinking exactly as we wanted to. At this point we've gone so far, and the only thing left is testing the circuit on a breadboard. Now this is the time we test the circuit on breadboard. To be honest, we're not going to do this for testing because I'm confident that the circuit is gonna work, but I'm doing this to show you how to connect this microcontroller on a breadboard and what components you're going to use. And the first thing we need here is a power supply, and I'm using a 12-volt power supply from my PC. And of course, we're not going to directly connect this to the microcontroller, or we're gonna have fried potatoes instead of a blinking LED circuit. So here is a 7805 voltage regulator IC, and I'm pretty sure that many of you guys have worked with this IC before. But for those who haven't, this IC can take any voltage between 7 and 30 volts roughly on the input pin here, and gives you a constant 5 volts on the output pin here. So this IC is popular and you can buy it from any supplier, but if you have a 5 volt supply, you don't have to use this IC. Just make sure that the supply you're using have a stable 5 volts output. So stating the obvious, this is the PIC18F 2550 microcontroller, and it's a deep package so we can mount it easily on the breadboard. Here is the 4 MHz oscillator. It has 2 pins. There is no polarity here, and the LED. Finally, a 330 ohm resistor, and since we're using it to light an LED, so don't get frustrated if you don't have this value. Even a 1K ohm resistor will be fine. So let's see how we can put all these components together to get the circuit working. First, we connect the voltage regulator. So we connected the 12 volt here to the input pin. Next, we connect the ground pin as the middle, and finally we connect the output pin to this 5 volt line here. So let's take it from another view here. Then we put the microcontroller on the breadboard, and let's see where we connect the 5 volts from the regulator and ground to the microcontroller. Here is the data sheet of the microcontroller. Here we have VDD, or the 5 volts, connected to pin number 20, and the ground is connected to pin number 19. And if you noticed, there is another VSS or ground pin here at pin number 8. So just to make sure that the ground is stable, and of course you can use either one of them, but we're going to use both since it's not a big deal to connect to grounds. And here's the oscillator is connected to pin number 9 and pin number 10. So let's see how we can connect them on breadboard. And here we go to the breadboard again, and we need to connect the pins we see on the data sheet and breadboard. So before doing this, we have to find pin number 1, and if you guys can see, there is a notch here, and this notch indicates that the pin number 1 is to the left of this notch, or as a dot here. So this is pin number 1, 2, 3, 4, 5, 6, 7, and 8. So we connect the ground as this pin. What I've did here is connecting pin number 8 to ground, then connecting pin number 19 to ground, and connecting pin number 20 to 5 volts line here. So, but if you remember guys, we haven't connected this line to ground. So I did a little trick here and connected a jumper wire from the ground pin on the regulator to the ground line here. So we have this blue line connected to 0 volts or ground, and the red line connected to 5 volts, of course. So, and the next thing we're gonna do is connecting the oscillator. Here is the oscillator, and it's connected to the pin directly after the ground. So here we go. Just make sure that you connect the oscillator as close as possible to the microcontroller pins. But there is one little thing I haven't mentioned, and it's we need 2 capacitors here, about 20 or 22 picofarad capacitors, to connect them to the between the oscillator and the ground pin. And why we need them? Just to have a stable clock source entering the microcontroller pin. So what I've did here is connecting one capacitor between pin number 9 and ground, and the other capacitor between pin number 10 and the ground. So now let's connect the LED. Here we connect the resistor at RB0, but we don't know where is RB0, so let's look at the data sheet. RB0 is exactly above VDD pin, or at pin number 21. So here we go and connect the resistor here. So then we have the LED. Just make sure that you connect the positive terminal here to the resistor and the negative terminal to ground. And by now we should have a working circuit, but of course I did a stupid thing as usual. I connected the microcontroller to the circuit even before uploading the code to the microcontroller. So we need to remove it from the circuit and show you how to upload code to the microcontroller. So here is a programmer I'm using to write code to PIC microcontrollers. This board is called PIC18F and there is PIC18F, but I prefer using this one. And you may not find the same exact kit on your local stores or on the internet. So if you get a different one, just read the data sheet and you can figure out how you can use it with your microcontroller. So let's insert the microcontroller here, close it, and there is a USB connector that you use to connect this board to your PC to write code to the microcontroller. And let's move to the software part and see how we can use this to upload code to PIC18F. So after connecting the kit to your PC, open this program here and you can download it from the link given in the description. Okay, open it, and to make sure that the programmer has recognized your device, you should see the name of the microcontroller here. If you see anything else, this means that there's either something wrong with the connection between the kit and your PC, or with you placing the microcontroller on the kit, which is bad news for your budget. And if everything is fine, click on File, Import Hex, and you should go to the hex file in the Blinky folder right here in the MPLAB projects, and blinky.x this default production, which is the hex file we uploaded in the simulation. Click on it and then write, I don't know what is this, and here we go. The program is successfully uploaded to the microcontroller. So disconnect it from your PC and place it on the breadboard again. So here we have the microcontroller back on the breadboard, and let's connect the power supply and pray for our project to work fine. Here it is, and we have the LED blinking as we want. That's it for now, guys. Don't forget to subscribe to my channel. Go ahead and click on the next video for a more detailed discussion on this code and another example to make sure you understand GPIO. Peace.